In this video, we're going to talk about unit circle trigonometry as well as special angle triangles. Periodic phenomena are frequent in our lives. When you have an event repeating over and over and over again, then it's like going around in circles, right? You keep doing it and doing it and doing it again. Think of a clock, right? It goes round and round and round and round and round in the same pattern every day. When that happens, we can actually depict the periodic behavior using a circle, because a circle is one way to show that something repeats in the same way over and over and over again. And we can have a relationship between the angles in the circle and the vertical, horizontal distance and the radius of a circle in relation to those angles of a circle. So let's see how we can connect all of those pieces in order to create the relationship that will determine the unit circle trigonometry. As we rotate around the circle, there are angles formed around it. And those angles start by placing the initial arm in the standard position where it falls right on the positive x-axis. Here, the angles are 0 degrees, and then each rotation is 360 degrees. 1/4 rotation is 90 degrees. 2/4 or half of a rotation is 180 degrees. 3/4 of a rotation is 270 degrees. Each one of these quarters is called quadrant. This is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. It's important to remember the quadrants order because they determine the sign of the ratio of each angle around the circle. Now, within the unit circle, we can create triangles. How? The triangles are formed by connecting the horizontal distance, the vertical distance, and the slant radius together at a certain central angle at the center of a circle. So if I draw a line like this, which is my radius here, and then I bring the vertical line down like this, which is the vertical distance, and then this is my horizontal distance, and there is an angle here, angle theta, then I can use this right angle triangle to determine the trig ratios of the given angle. So sine of theta will be opposite over hypotenuse, y over r. Cosine theta will be adjacent over hypotenuse, x over r. And tangent theta will be opposite over adjacent, y over x. The theta angle is called related acute angle, and it's located in quadrant 1. In fact, any angle in the quadrant 1 is a related acute angle. Why is it called related acute angle? Because I can translate that angle to any other quadrant. For example, if I create a reflection of that same triangle here, then angle at the center, at the origin here, is still theta. These two angles are identical. However, every time I measure the angle, I start at the positive x-axis. So now my actual principal angle is this angle right here that is based on the original related acute angle. And what is really special about them is that they share the same value of any one of the trig ratios. So sine of this angle will equal sine of this principal angle, only with a different sign, positive or negative. The sign of each ratio is determined by its location within the quadrants. So in quadrant 1, all ratios are positive. In quadrant 2, only sine ratio is positive. In quadrant 3, only tangent ratio is positive. And in quadrant 4, cosine ratio is positive. All other ratios will be negative. So if I wanted to determine the sine ratio of the principal angle here, it will equal the same value as the sine ratio of this related acute angle, but negative, because sine is negative in quadrant 3, only tangent is positive. How do we determine the ratios of some of the most common angles? We use special angle triangles for that, and we form them in the first quadrant, just like this one. Let's look at those special angle triangles. So there are two special angle triangles, and they are based on the angles of 30, 60, and 90, and 45, 45, 90. All of these angles are acute angles, and on a unit circle, they will be found in quadrant 1. These triangles would also be formed in quadrant 1. Why are they special? Because we can determine the exact trigonometric ratios for these particular triangles and for these particular angles. Let's look at them. So the side length that are being created by these angles and the ratios within the trig unit circle are the following. The side beside or adjacent to the 60-degree angle is equal to 1. The hypotenuse is equal to 2. And this side here is equal to square root of 3. It helps to memorize these ratios because it saves time and it helps you determine the exact values, not approximate decimal values. And within the other triangle, this side is 1, this side is also 1, and the hypotenuse is square root of 2. From each one of these, we can determine the exact trig ratio of each one of the angles here. So if I wanted to, say, determine sine of 45 degrees, then I will do opposite over hypotenuse, 1 over square root of 2. If I wanted to do cosine of 45 degrees, it turns out to be the exact same value. And tangent of 45 degrees is opposite over adjacent, which is just 1. If I wanted to determine sine of 30 degrees based on this special angle triangle, it's equal to opposite over hypotenuse, and opposite side to 30 is 1, hypotenuse is 2, so it's 1 over 2. If I wanted to do sine of 60 degrees, the opposite side to 60 is square root of 3, so square root of 3 over hypotenuse of 2. If I wanted to do cos 30, it's equal to adjacent over hypotenuse, square root of 3 over 2. And cosine 60 is equal to 1 over 2. Then tangent of 30 degrees is equal to opposite over adjacent, 1 over square root of 3. And tangent of 60 is equal to just square root of 3. Now let's see how we can use all of the information that we have just learned to determine the trig ratio of one of the principal angles. Say I want to determine the sine ratio of 210 degree angle. What is it equal to? So first, decide which quadrant the 210 degree angle is located in. It's between 180 and 270. Therefore, it's somewhere here in quadrant 3. We start the angle right at the x-axis in its positive side and rotate all the way around until we reach the 210 degree portion. Now, we've located it in the third quadrant. The next step is we need to determine what the related acute angle is for the 210 degree angle. For that, we need to take the closest horizontal angle on the horizontal axis and either add or subtract to it. So we have 180 and we have a principal angle of 210. What is the difference? What is this difference between them? Between 210 and 180? That will be our RAA, related acute angle. So 210 subtract 180, and this gives us 30 degrees. So related acute angle that could be translated into this quadrant as well is 30 degrees. Why is it important? Because now we can use a special angle triangle, the 30, 60, 91, to determine the exact trig ratio of the 30 degree angle and consequently of the principal angle that is based on it. So if I take the special triangle of 30, 60, 90, and I have my sides 1, square root of 3, and 2, then I can say that sine ratio of 30 degrees is equal to opposite over hypotenuse, 1 over 2. Then the value of the sine ratio of 210 degree angle will be the same. The only thing that will be different or might be different is the sign of the ratio. Since the 210 degree angle is in quadrant 3, and in quadrant 3 only tangent ratio is positive, the rest are negative, I have to state that sine of 210-degree angle is equal to negative 1 over 2. The same value as the ratio of a 30-degree angle of the related acute angle with the opposite sign. There are other 4 special angles, and they are right on the axes. So there is a 0-degree angle or 360-degree angle. There is a 90-degree angle, 180, and 270. How do we determine the ratios for them? Remember that ratio is the relationship between the vertical distance, the horizontal distance, and the radius. In the case of horizontal and vertical angles that fall right onto the axis, the horizontal or vertical distance will either equal to 1 or 0. And the 1 distance will also coincide with the radius. For example, if I look at this angle here, there is no vertical distance, right? There is no vertical change here. The line is right on the horizontal axis. Therefore, the opposite side is 0. And if I wanted to determine the sine ratio of this angle, the opposite side would be 0. The adjacent side would be 1 because this is a unit circle with a radius of 1, and the radius is 1, which is the hypotenuse of a triangle. So then I will divide 0 by 1, and it will be equal to 0. Sine of 0 is 0. Cosine, which is a horizontal distance, and the adjacent side to the angle at the center will be 1. The hypotenuse, or the radius, is also 1. So cosine of this angle will equal to 1. On the other hand here, cosine will equal to negative 1. But sine, that is based on the vertical distance, is equal to 0. For a 90-degree angle, sine ratio is equal to 1, cosine is equal to 0. For 270-degree angle, sine is equal to negative 1, cosine is equal to 0. The tangent ratio for the 90-degree angle and the 270-degree angle is undefined. And for 180 and 0, 360, the tangent ratio is equal to 0. When you rotate around the circle, you can make unlimited amount of rotations, right? The angles will repeat and they will add up. So if I have a 0-degree here and I make a rotation of 360, I will go back to the same position. So the new angle will be 360 degrees. And then if I rotate again, I will do 360 plus 360. And that's another rotation, and it forms a new angle. So when you make a rotation, you call it a period. And when you create a new angle by adding a period to the previous one, the new angle is called coterminal angle. So 0 degrees and 360 degrees are coterminal angles. They are two angles that fall in the same position, but through a different number of rotations. 0 rotations, 1 rotation. And if I keep adding the rotations, the periods, the new angles will be created, but they will always end up in the same position. coterminal angles.